You know that scene, right? The detective hunched over a monitor looking at some grainy security footage, and they say that magic word, enhance. And just like that, this blurry blob sharpens into a perfect, crystal clear image, revealing the killer clue. For decades, that was just pure science fiction. But what if I told you that fantasy, it's now a powerful, world-changing reality? So here's how we're going to break it all down. First, we'll separate the Hollywood hype from the actual science. Then, we'll dig into why this is such a tough nut to crack for computers and how a breakthrough called deep learning basically taught machines how to see. After that, we'll look at the incredible ways it's being used in the real world. And we'll finish with a surprisingly deep question. What does a better image even mean? Okay, first up, fantasy versus reality. Let's put that famous movie moment right under the microscope. Right, that classic command. You've seen it in Blade Runner, you've seen it in a million episodes of CSI. But the real question has always been, can you just create information that isn't there? Can you really pull a license plate number out of a few blurry pixels? I mean, the goal is pretty straightforward. You want to go from this, a low-res image where all the good stuff is lost in a pixelated mess, to this, a high-resolution version where those details are sharp, clear, and look totally real. For the longest time, this was just impossible. But here's the thing. Today, the technology is real. No, it's not magic, but it's probably the next best thing. And it has a proper name in the world of computer science: image super resolution. But actually doing this is way harder than it sounds, which brings us to the super resolution challenge, one of the trickiest problems in all of computer vision. So, just to be super clear, image super resolution, we'll just call it SR, is the process of taking a low-resolution image and recovering a high-resolution version from it. Simple enough on paper, right? Well, not quite. The reason this is so mind-bendingly difficult is because it's what scientists call an ill-posed problem. So what on earth does ill-posed mean? Well, think about it like this. A single blurry patch in a photo could have been made from almost anything, right? Was that patch originally blades of grass, the texture on a brick wall, a pattern on someone's sweater? There are tons of possibilities. And because there's no single right answer, a computer can't just solve it with a formula. It has to make a very, very educated guess. So if it's basically a guess, how do computers get it right? Well, that takes us to the big breakthrough: teaching an AI how to see. Or maybe more accurately, how to intelligently hallucinate all those missing details. And that breakthrough came from this area of AI called deep learning. You know, the best way to think about one of these super resolution AIs is to imagine it's a digital artist, an artist who has spent its entire life studying millions and millions of blurry photos next to their sharp originals, just learning the relationship between them. So how does this digital artist actually learn its craft? It's a really simple but super powerful four-step loop. First, you just feed the AI tons of examples, a blurry pic and its sharp counterpart. Second, the AI takes a shot. It makes its best guess at turning the blurry one sharp. Third, it compares its version to the real deal and calculates how wrong it was. We call that the error. And finally, this is the magic part, it tweaks its own brain a little bit to make a better guess next time. Now do that millions of times, and pretty soon, it becomes a master at restoring images. Okay, this is where all that theory gets real. Let's jump to section 4 and see how super resolution is moving out of the lab and is literally changing how we see our entire planet. This tech has gotten ridiculously powerful. Today's best commercial satellites can get a resolution of 30 centimeters per pixel. Now, to put that in perspective, that means a single dot of light from space represents something on the ground that's only about the width of a shoebox. It's small enough to easily spot individual cars or shipping containers from orbit. And when you have that kind of detail, the real-world uses are just incredible. City planners can create these amazingly detailed maps for new buildings and roads. After a wildfire or a flood, emergency teams can see the damage in places nobody can physically get to. Farmers can monitor the health of their crops with almost surgical precision. And conservation groups can track things like illegal logging, all from space. And look, this isn't just some cool tech toy. It is incredibly valuable. I mean, the data speaks for itself. There is a direct and very steep connection between how sharp an image is and how much it costs. A 30-centimeter image can cost almost 10 times more than a 2-meter one. And why is that? It's simple. Sharper images give you better data, and better data is worth a whole lot of money. But all this brings us to a really fascinating and kind of tricky final section. What does better actually mean here? Because it turns out there's a surprising conflict between what a computer considers a perfect image and what our human eyes do. So you have these two competing ideas of what's good. On one side, you've got mathematical accuracy. This is all about getting a perfect pixel-for-pixel match to the original. But the weird thing is, these perfect images can often look a little too smooth, almost blurry to us. Then, on the other side, you have perceptual quality. This is what a different kind of AI, called a GAN, aims for. Its only goal is to make something that looks totally, 100% photorealistic. And they look amazing. But to pull that off, the AI might have to cleverly invent plausible details, like the texture on a leaf or a reflection in a window, that weren't actually there. And this isn't just some vague idea, it's a real technical trade-off. As a group of researchers put it back in 2018, distortion and perceptual quality are at odds with each other. What they're saying is, you can have an image that's mathematically perfect, or one that looks real to a person, but it is incredibly hard to get both at the very same time. And this leaves us with a pretty deep final question to chew on. As these AI models get better and better at creating perfectly photorealistic images, not just enhancing them, but making them up from scratch, how are we going to navigate a world where we can't be sure if what we're looking at is a real photo or just a beautifully rendered guess?